All right, so welcome to lesson 5. This is the last lesson in our Introduction to Probability unit. We've already looked at, single events, and then we've looked at compound events in how they can be independent of each other or dependent upon one another. And we've also looked at some conditional probabilities. But now we want to also look at mutually exclusive and non-mutually exclusive events. So this should sort of remind us of Venn diagrams. Okay, so let's look back and think about, two different events, event A and event B. If they had any overlap where, oh, it's possible to be both A and B, like it's possible to be a queen and a heart. That overlap we called the intersection. And we noted that if you just wanted to find, A or B or both, that was our union. So we had a couple ways to do that. If we had the Venn diagram and we populated it, then we could just take the number that were in A only, plus the number that were in B only, plus that little intersection. And when you add all those together, those three values, that would give us the union or the number that were in A or B. Or if we hadn't populated the Venn diagram, we could just use the principle of inclusion and exclusion and take the number in A overall plus the number in B overall, and then just subtract out the intersection, which we had double counted, right? So these methods, either one, whether you populate it and add them singly, or whether you add them and then subtract out the intersection, they allow us to find the number of outcomes where event A and B could happen without double counting. Now, here we were just counting. It was cardinality, like how many ways can we do this? But now we're going to just do the same thing, and you can imagine it's no different. If you change those n's into p's, then the probability that A or B could happen is just going to be the same kind of procedure. So we're going to use the exact same methods that we learned in Venn diagrams to help us count probabilities where there may be some probabilities where, oh, I guess you could actually be both. There could be some overlap.
So mutually exclusive events. So really, we've looked at lots of Venn diagrams, and almost all the Venn diagrams we've looked at have been where they have
the circles overlap,
right, which is non-mutually exclusive. So the first thing that I think we should do here is we could say, okay, so first of all, let's talk a little bit more about mutually exclusive events. These are events that cannot occur simultaneously. As we've talked about in permutations, we talked about it in combinations, and now we're talking about it in probability. So they're basically events that cannot occur at the same time. So if one event has occurred, it is not possible that the second occurred at the same time. So remember when we were choosing in Unit 1, where we were choosing our outfits for the co-op job that we had, where you can't simultaneously wear a tie and not wear a tie. Those events are mutually exclusive.
So then we could use the additive counting principle, right?
So the Venn diagram for this, which we actually have never shown.
We've never seen one before.
Looks like this.
Whoa.
It's basically our universal set, and then our two events, A and B, with no overlap. There's no way the number of outfits in the one circle can overlap with the number of outfits in the second circle, because there's just no way that these two events can occur at the same time. And so what are some other examples of mutually exclusive events?
Okay, so let's say you roll a die one time. The probability of getting a 1 and a 2. Well, if you only rolled it one time, you can only get a 1 or a 2. So they're separate things. They'd be separate circles inside your universal set. Getting a sum of 3, okay, which would be a 2 and a 1, and 2 of a kind, which would be pairs, like 1s, 2s, 3s. Well, you can't do that. Like if you have a pair of dice and you roll them one time, you couldn't simultaneously get a sum of 3 and a pair. Okay, so those would be mutually exclusive. If you wanted to remove a queen and an ace, well, you can't be both a queen and an ace. If we said a queen and a heart, maybe, you could be both a queen and a heart, but you can't be a queen and an ace at the same time. So those are separate things that can't happen. If you were to just take one card out, there's no way it could be both a queen and an ace. Okay?
So we have a rule, the addition rule for mutually exclusive events. Basically, we look at if two events are mutually exclusive, i.e. the probability of the first event and the probability of the second event, and there's no intersection, we add these probabilities together. And again, it's linked to this word or, right? So the probability of A or B is equal to the probability of A plus the probability of B when events are mutually exclusive.
So if you can't picture any situation where your thing could simultaneously be both of those conditions, then picture that split apart pair of circles
Mhm.
where there's no
Mhm.
overlap. So those
This
are
is
mutually
this is
exclusive.
what we do with cases as well, actually.
Yeah.
When we have cases, we set them up so that we have mutually exclusive cases,
Yeah.
and then we add those cases together.
Yeah.
Okay, so here's example number 1. If 2 standard dice are rolled, what's the probability of rolling doubles or a total of 11? So what we want to say is here, let's define the events. A is the event of rolling doubles.
Yeah.
And B would be the event of rolling
A
an
sum
11.
of 11.
Yeah, sum of 11.
Yep.
So it's really helpful if we go back and look at our 6x6,
Yeah.
our dice chart,
Yeah.
right? And so what we can see here is that we have highlighted all the doubles in red, or I guess it's pink, I
Pinky
guess.
peach?
Dusty rose.
Dusty
Dusty
rose,
rose.
definitely.
And we've highlighted the event of rolling a total of 11
Mint
in
green.
green. In mint green. And so what we can say then is that, okay, well, the probability of rolling doubles then, there's 6 possible outcomes for that, 6 in 36.
Yep.
And the event of rolling a total of 11, well, there's only 2 ways that we can do that, a 5 and a 6, or a 6 and a 5.
And we should note that there's no overlap here. The dusty rose and the mint green, they don't overlap.
Yeah.
And so we know that these are mutually exclusive because you can't simultaneously be a double and be a sum of 11. So now we know we can just safely add them up without having to worry about double counting or intersections or anything.
Mm-hmm. And so we say, okay, well, the probability of A or B is 6 in 36 plus 2 in 36. So we get a total of 8 in 36.
Sure.
Okay. So here we have a committee of 5 in example 2, and this committee of 5 is to be randomly chosen from 6 males and from 8 females. So what's the probability that the committee will either be all male or all female? Okay. So we should say before we begin, of course, that out of these 6 males and 8 females, these are people who have identified as being either male or female. So we don't have to worry. This is an example of a mutually exclusive event because even transgender people are going to identify as either male or female. So this really comes down to an example of a mutually exclusive event because we have identified as being 6 males on a committee and 8 females on a committee. So we've kind of still got those 2 piles and they're mutually exclusive.
The male pile and the female pile, they've checked off the checkbox. Yes, I'm male, or yes, I'm female.
So here we need to know what the probability is then that the committee will be either all male or all female. And this is actually a nice little example because we have to use counting principles to do this.
Right, because, well, and first of all, you can't have a committee that's all male and all female at the same time, so we know it's mutually exclusive.
Exactly.
We've got 14 people all together, so let's say we, in general, the no restrictions way of doing this, that would tend to be our Part 8 questions back in Unit 2, would be, okay, you got 6 males and 8 females, you want a committee of 5, with no restrictions, there's 14 people total, put them in piles, stir them up, and take out 5 people for your committee. So we know we're going to be dealing with combinations because order doesn't matter, right? We just want those people to be on the committee. We don't care what order. They're not particular positions like president, vice president, so we don't have to worry about order mattering. So let's just define event A as being the event that the committee is all males, and define event B as being the event that the committee is all females. And to be all males, in your 2 piles, your male pile, which are 6, and your female pile, which are 8, you're going to take 5 of the 6 and none of the 8. Right?
Exactly.
So when we do that as a probability, up there we see the 6 choose 5. You don't see the times 8 choose 0 because that just comes out to 1. 8 choose
0 is 1, yeah.
So, we're just saying, all right, I'm going to take all 5 of them from the 6 males over the sample space, which is, all 14 people. We don't care who's who. We don't care which gender. We're going to just take 5 of them.
Yeah. Okay, so we get 6 choose 5 over 14 choose 5. And we come up with a probability of 6 out of 2002.
Yeah, that's not very
Small
big.
probability.
Small probability.
All right, so the probability of all females, we've got 8 choose 5. And then we'd also be multiplying by 6 choose 0. But again, 6 choose 0 is 1 because we're not taking any males. Divide by 14 choose 5 is again 56 over 2002.
Higher probability because there are more females to choose from out of those 14.
Yes, exactly.
Yeah.
Now, the reality is that because we've defined these very carefully as being mutually exclusive events, we can use our addition rule for mutually exclusive events. We get 6 over 2002, plus we've got 56 over 2002, and what we get is 62 over 2002, which basically breaks down to about a 3.1% probability.
Sure.
So, what are non-mutually exclusive cases?
Okay, so now let's contrast. Mutually exclusive, we've been working on this, and every time you set up your own cases, by design, you're always setting up mutually exclusive cases, right?
Mhm.
So here, let's look at some non-mutually exclusive events. These are ones that could actually occur simultaneously.
Mhm.
You know, if you have one condition met, it is quite possible that, oh, the other condition could be met at the exact same time.
Mhm.
And recall that very first example we did in Unit 1 there, where we said, what's the probability of getting, you know, a queen or a heart? And we're like, oh, well, you can be a queen and not a heart. You can be
Mhm.
a heart and not a queen, but you can also be a queen of hearts.
Mhm.
And so, you know, you're like, oh, well, I guess, you know, you can see that there is an area of overlap. There is a possibility that an outcome could be simultaneously both of those things. And
Mhm.
so that is what makes that a non-mutually exclusive event. So a couple more examples. And what this looks like, this is like the typical Venn diagram that we
Yes,
would see,
where we see overlap.
where you've got the queens not hearts on the left side, the hearts not queens on the right side, and then that queen of heart is that
Mhm.
one in the middle,
Is
right?
that one in the middle?
Because you can simultaneously be a queen and a heart. So here's some other examples of things that are non-mutually exclusive. We're like, oh yeah, you could actually get an event where both those things happen.
Mhm.
Getting a 1 or a 2 on two rolls of a die. Yeah,
Mhm.
I could actually get a 1 on the first and the 2 on the second, or a 2 on the first and the 1 on the second.
Mhm.
I could do that, right?
Mhm.
Getting a sum of 4 or 2 of a kind. Like, oh, well, 2 of a kind would be a pair of 2s.
Yeah.
The
Or
sum
you
of
could, yeah.
4 would be a pair of 2s or a 3 and a 1 or a 1 and a 3.
Yeah.
So now we're like, oh,
Yeah.
we don't want to double count because there is going to be an event that can meet both of those
Yes.
criteria. And then removing a king or a spade. Well, sure, there are
Yeah.
kings that aren't spades, and sure, there are spades that aren't kings, but there's that one king of spades where if we don't consider him, we have double counted him.
Yes. So here's the addition rule for non-mutually exclusive events, and this should look strikingly similar to the rule of inclusion and exclusion.
And it's the union. If we
Yeah.
replace that word or with that horseshoe-shaped U,
Yeah. Yeah.
then we are looking at, like, what's the probability of this or both, no double counting.
Yeah, so it's the
Right?
probability of A plus the probability of B minus the probability of A and B where we've double counted.
Yep.
Okay, so let's take a look at a few examples. If 2 standard dice are rolled, what is the probability of rolling doubles or a total of 10? So in the first time we did this, it was a total of 11.
Yeah.
Right, so now it's, hey, what's the probability of rolling doubles or a total of 10?
Well, let's define some events here.
Yeah.
So A is the event of rolling doubles. Sure, B is the event of rolling a sum of 10. Okay. Maybe let's look at that 6x6 grid, and we've re-highlighted the doubles in pink. We've highlighted all of the, you know, sums of 10 in green, but then that double, you know, intersection, that overlap where you could be 2 5s and also be a sum of 10, that is the one where if we didn't consider it, we would repeat it. We'd have double counted it, right? So you can simultaneously be a double and a 10. So that means picture the normal Venn diagram with the overlapped circles, and we're going to have to use, you know, our counting principles that we know.
Yeah,
for that.
exactly.
Yeah.
So here we've got the probability of rolling doubles, as we said before. There's 6 possible ways to roll doubles,
Yep.
6 and 36. The ways that we can roll a 10, well, there are 3 ways, a 6 and a 4, a 5 and a 5, or a 4 and a 6.
Yeah.
So there are 3 ways of rolling a 10. There are exactly 1 way of rolling doubles and a total of 10, and that's the case where we roll a 5 and a 5.
Yep. So that's our little blue overlap.
Right? Yep, exactly.
Yep.
And there's a 1 in 36 chance of doing that.
Yep.
So the probability of A or B of rolling doubles or a total of 10 is probability of A plus the probability of B minus the probability of both. And this is our addition rule for non-mutually exclusive events. We can sub in our values here, and what we find is an 8 in 36 chance.
Yep.
Again, 2 and 9.
Yep.
Okay. Last example here. Card is randomly selected from a standard deck of cards. What is the probability that either a red card or a face card will be selected?
Okay. So we have to first ask ourselves, could you simultaneously be a red face?
And the answer would be yes.
Yes. So
Okay.
we're picturing, again, a Venn diagram with 2 circles where there is an area of overlap. So we know this is non-mutually exclusive, right?
That's
So
right.
we're going to have to consider a little bit of extra work for doing our principle of addition there.
Yeah. So here's probability that we pull a red card, and it's half. It's 26 red cards out of 52 in the deck.
Sure.
Here's the probability that it's a face card. Well, we know that there's 12 face cards in a deck, so that would be 12 in 52.
Yeah.
So what is the probability that we would pull either a red card or a face card? Well, in order to do that, we need to consider the number of face
red
cards,
face cards
that are also red.
Yeah.
Exactly.
Yeah.
And here they are. We've just kind of diagrammed them out. The face cards that happen to be red. Okay, and there's 6 of them.
Yep.
6 and 52. So basically what we'd say is the probability of red or face is probability of A plus probability of B minus the time that we would double count.
Yep.
And so what we get is 26 plus 12 minus 6 all over 52. So we get about 8 in 13, or a 62% chance.
Yep.
Okay. Now, we're going to do another example, but really what I would like to do now is actually include a Venn diagram in the solution so that we can kind of see how that works. So let's take a look at example number 5 then.
Okay, so let's say we're in Statsville. Probability of a teenager listening to classic rock is 42%. The probability of listening to the New Country station is 36%. If 13% of the teenagers surveyed listen to both stations, okay, what is the probability that a given student listens to neither? So again, if you're picturing this, there is an overlap. There's that 13% overlap. You've got classic rock and New Country, but there have got to be some teenagers who are not listening to either of those.
That's not possible.
And so we want to basically find, you know that gym analogy where you're in the gym and there's people standing in the hula hoops, and who's in the gym but not in the hula hoops. We're trying to figure out basically the complement to this union.
Yeah.
Like, 1 minus the probability of listening to classic rock or New Country, right?
So we'll set our event definitions.
Okay.
And here they are. A is the event of a student listening to classic rock, and B is the event of a student listening to New Country. And so basically what we're going to do is we can use, again, this is our rule of addition for non-mutually exclusive events, which also happens to be the rule of inclusion and exclusion. Right?
Yeah. If we change the P's to N's, it would just be simply the principle of inclusion and exclusion.
So basically we've got 42% or 0.42 listen to classic rock, 0.36 listen to New Country, minus the 0.13 who listen to both. And what we end up with is 65% of students listen to either A or B.
Yeah.
Okay. So how many students then listen to neither? Well, what we actually want is the probability of not A nor B, which is exactly the complement of A or B. So 1 minus 0.65. So there are 35% of students that listen to neither. And what we can do then is we can say, hey, this probability is 35%, and we can diagram this using a Venn diagram. So we've got the event A, and we've got the event B, which represent our 2 circles.
Now what we want to do is, just like we've always done, is we want to start by populating the Venn diagram with that intersection.
And we can do that because we know that there's 13% of students that are in here. Now keep in mind, this is a probability Venn diagram, so we're just using percentages in here rather than the number of actual students. So here's 13%. The number that listened to classic rock was 42%, but the number that listened to only classic rock would be that 42% minus this 13% that we've already counted. So we get 0.29%. Or sorry, excuse me, I should say 0.29 or 29%. Here, the number of students that listen to only New Country but not both would be 0.23. And of course that's just 0.36 minus this 0.13.
And when you add these 3 values up,
this plus this plus this,
you get your 0.65, right?
And so we can place our 0.35 students on the outside. Okay. So at Waterloo West Animal Hospital, this is our dog, Mr. Jackson's dog. This is Pipper, and where we take Pipper, basically the vet has found that he's going to require his teeth cleaned with a probability of 0.6, his fur clipped with a probability of 0.3, and both with a probability of 0.1. Right. So a Venn diagram in this case is going to be helpful. So we'll do one. Here's the 3 questions. What's the probability that Pipper needs either his teeth cleaned or his fur clipped?
Okay, so we're looking for the union there.
What's the probability that he needs his teeth cleaned but not his fur clipped?
Okay, so teeth only, not fur.
And what's the probability that I could actually walk into the vet's office and not pay for either of these things?
Yeah, just a normal checkup. All right.
Okay, so basically T is going to be the event of having his teeth cleaned. F is going to be the event of having his fur clipped. Here's our Venn diagram with T and F as our events. And so what we have is we have a 0.1 probability that he's going to require both of these things that was given in the problem.
Yeah.
His teeth cleaned, we have a 0.6 probability,
Altogether.
but we've already placed the 0.1. So this is going to be a 0.5 out here.
Yep.
And the fur clip is basically 0.3, but again, we've already placed 0.1 in here, so we got a 20% probability out here.
Yep.
All right. So really, we can look at this Venn diagram. We can probably answer C almost right away.
Yeah, we can answer all. Now that we've
Right?
populated
Now that we've
the Venn
done this,
diagram,
we can do
we're
it.
good to go. So if we want to know A, probability of teeth cleaned or fur clipped, well then that's just going to be the probability of teeth plus the probability of fur minus the probability of teeth and fur, which
Yep.
we can do just using the numbers, 0.6 plus 0.3 minus 0.1. Or we could go to the Venn diagram, and remember you could add
Yeah.
T only plus F only plus T and F, right? And that'll also give you 0.8.
Mm-hmm.
Okay.
So there it is. Part B, basically there's an 80% chance he needs either his teeth cleaned or his fur
You're
clipped.
paying for something extra.
Yeah, it's a high
happen.
probability.
Sorry, Mr. Jackson.
Yeah. Here again, let's just save our Venn diagram. And so basically in B, let's use the Venn diagram to see that, hey, the probability that he needs his teeth cleaned but not his fur clipped would be the 0.6 of the teeth being cleaned minus this little section right here where we've double counted. So really all I want is this section
Just
in
teeth
here.
cleaned. Yep.
So 0.6 minus 0.1 is 0.5, and we can see that. That's right in this Venn diagram here. If I'm trying to find the probability that I can walk in here and not pay for anything, you know, no teeth cleaning, no fur clipping, just the basic checkup, the sum of all the probabilities is 1. So there is a number that's residing out here, because inside of this box in the universal set, all the decimals, all these have to add up to 1.
Yeah, because probabilities of all possible outcomes add up to 1.
To 1.
Yeah.
And so basically what we can say is, well, 1 minus the 0.8 that we've accounted for is 0.2. So there is a 20% chance that Pipper needs neither.
Oh, Pipper.